Section 9.2, we're going to continue extending our understanding of inequalities beyond what we learned in Algebra 1. The type of thing we're going to be talking about today, we're still going to be limiting ourselves to linear inequalities, but we're going to be combining them in strange and complicated ways to sort of prepare you for the trickier nonlinear inequalities that are coming in the future. So there are really three situations that we need to learn to deal with here in 9.2. The first situation is something like this example, where the inequality has three pieces. There's a middle piece, and a left piece, and a right piece. This sort of situation comes typically in the English language when you use the word between. Here you would say x plus 2 over negative 5 is between negative 2 and 6. That means it's bigger than negative 2. It means it's also less than 6 at the same time. So the word between typically gives you one of these three-sided inequalities. Now, the English language, and this isn't just English, it's pretty much all human languages, they don't do a good job of differentiating between greater than versus greater than or equal to, or less than versus less than or equal to. So, although the word between gives you something like this inequality is a truly mathematical thing and it has more data in it than just that. The technique for solving this is not a new technique. You've learned how to solve linear inequalities before. Three-sided linear inequalities work the same way. For example, one of the techniques that you learn with regular inequalities is to clear out fractions by multiplying by the denominator. That means we're going to multiply everything times negative 5 here. Make sure you don't lose track of the fact that there's a left, a middle, and a right. That's one weird mistake that students make a lot, where they're just so used to two-sided inequalities that their mind just has like a blank spot where it just doesn't see the 6 or it just doesn't see the negative 2. There are three sides here. If you don't have a left, middle, and a right, something is missing. So we multiply through by negative 5, and that gives us 10 x plus 2 and negative 30. But don't forget, since we multiplied by a negative, that means the inequality symbols have to change direction, and that's true for both of them. So it's greater than or equal to now. The next thing that you would probably want to do is subtract 2 to get x by itself. Make sure you subtract 2 on both sides. Oh, wait a sec. Both. There are three sides. Subtract 2 on all three sides. So now you've got 8 greater than x greater than or equal to negative 32. And then you have to interpret the answer. And sometimes that's the trickiest part of these problems, is not getting to the answer, but then interpreting the answer and knowing what it means. So here, the two common sorts of things that you'll be expected to do with this type of an answer is to either graph the answer on a number line. And that's a pretty common one because a lot of people are very visual thinkers and they want to see the answer. But another answer that's very, very common is interval notation. In fact, I bet that one's more common. You'll see that in just about every textbook in most classes, almost every professor. So on a number line, make sure you don't make the really basic mistake of drawing a picture like this. I would take a lot of credit off for a mistake like that. 8 is not smaller than negative 32. Smaller numbers are on the left of the number line. Larger numbers are to the right on the number line. So if you set up your number line fundamentally wrong like that, expect to lose a lot of credit. That's not the kind of mistake that you should be making if you're in Algebra 2. Negative 32 is the smaller number. 8 is the bigger number. That's how those points on the number line should be arranged. And x has to be smaller than 8 and bigger than negative 32, that means it should be in between. Notice the word between still applies. It's allowed to equal the negative 32. It's not allowed to equal the 8. And the symbols that I'm familiar with, that I prefer, are the dot symbols. they seem to be less common now than they used to be. People are shifting over to sort of an interval notation symbol on a graph, and I've always thought that looked like some weird hodgepodge, so I prefer the dot notation, and if you like the dot notation, you can use the dot notation too. Interval notation would be fairly straightforward. It's the interval from negative 32 to 8, with a bracket on the negative 32 because that one's included, and a round parentheses on the 8 because that one's not. So these three-sided inequalities will be pretty simple because you solve them just like regular inequalities, and although the interpreting the answer business at the end is a little tricky, as long as you remember the word between is what's going on here, you'll probably have very little trouble getting the right answer at the end. So the other two situations we have to learn today have to do with using the word and using the word or. So, first of all, these will be problems that involve two inequalities. There will be an inequality on the left, and it'll be a normal linear one. There will be an inequality on the right, and it'll be a normal linear one. And then there will be a word in the middle, and the word will either be and or it'll be or. In fact, for comparison, we're going to do the same problem a second time in one moment, where the only change is going to be I'm going to have the word and in the middle instead of the word or. And we're going to see what the comparison is. So first of all, solve each individual inequality. And I really sort of gave a slow pitch here. This is a very easy one. The only inequality that needs any work at all is this one. Multiply both sides by -1, and don't forget to change the direction of your inequality, and you're done solving. The left-hand inequality doesn't need any work at all. And then, what I suggest that you do next is draw a picture of each inequality. Make sure you get your key numbers in the right order, just like I said a second ago. That's kind of important. This one should be a graph of numbers below or equal to -7, so that should look like this. This one here should be a graph of stuff that's bigger than -1, so it would look like that. And then, when you've got the word or, what that means is you're going to include all of the answers. You're going to include anything that's green, that's a solution, or all the stuff that's blue, those are solutions too. So, if you see the word or, what you're supposed to do is include everything. So your answer here is all of that and all of that. In interval notation, you have a little bit of a challenge because there's two intervals here. There's an interval that includes -7. I wrote that 7 really weird. There we go. And there's an interval from -1 to infinity. So the interval notation has this union symbol in between to say I'm including all of that. Now for comparison, over here on the right, the solving would be identical. I'm not even going to show it. You're going to get x less than or equal to -7, x greater than -1. When you draw the two inequalities, you would get the same picture there. You would have -7 below. You would have bigger than -1 like that. But the word and means a very different thing from the word or. And means you're looking for points that are green and blue at the same time. In other words, to use a simpler word, and means use the overlap. And if you look at this picture, there's no overlap. There are no numbers that are both less than or equal to -7 and at the same time also bigger than -1. So in a situation like this, where there's no overlap at all, the answer I would provide would be no solution, and that is a possibility. Now we need to take a look at tricky cases. I've shown you basically what the word or means and basically what the word and means. But it turns out that even if you understand what those words mean, there's still some pretty tricky situations to look at. So here's an example. And again, the way you begin is fairly straightforward. Just solve each inequality the normal way. So here I'm going to subtract 3 from both sides and get a is less than or equal to negative 5. And here I'm also going to subtract 3 from both sides, and I'll get a is less than negative 1. And then I'll do like I did a second ago, and I'll graph each one of these inequalities in its own separate color. So I'll do this one in green. A less than or equal to negative 5 looks like that. I'll do this one in blue. A less than or equal to negative 1 looks like this. And when you use the word and here, remember, and means overlap. And if you look at these two graphs overlap only over here below negative 5. Here in the middle, you don't have overlap. You only have one inequality working and not the other. And over here on the right, you have none of them working. So the solution set for this pair of inequalities would be just this. It's almost as if that second inequality didn't do anything. And if you think about it, it doesn't do anything. If you already have numbers that are smaller than negative 5, throwing in they also have to be smaller than negative 1, that's automatic. It doesn't restrict things any further. Take a second and consider, what if the word in the middle was or? Well, now you do a very different thing. Same picture, same green set, same blue set, but the difference is now you take everything. And if you take everything, you're going to go all the way up to negative 1. So the same two inequalities, just change the word and versus or, makes a change like that to the answer. Here's another tricky example. Take a second to solve each one, press pause, see if you get the same answer I'm going to get. All right, when you solve this one, you get b greater than negative 1. When you solve this one, you get b less than or equal to 4. And when you graph this, make sure you get your key points in the proper order. Negative 1's over there, 4's over there. Do this one in green. So greater than negative 1 looks like this. I'll do this one in red. Less than or equal to 4 looks like that. And we're using the word or. Or means take everything. It doesn't matter if it's green and red, or just green. You take everything, and in this case, that's literally everything. So the solution set here would go from negative infinity to infinity. And if you like fancy symbols, the fancy symbol for the solution set here is a double capital R. That's the real number set symbol. So this is a very strange situation. Everything is a solution. Everything is either red or green or both. And then one last example to work out. Again, press pause and see if you get the same answer I'm going to get here. All right. Solve this one down. You get t is bigger than or equal to 3. Solve this one down. You get t is less than or equal to 3. And if you graph that, you only have one boundary point. This one, t greater than or equal to 3, is all of those numbers. This one, t less than or equal to 3, is all of those numbers. And remember the word and means overlap. There's only the tiniest little bit of overlap here. These two colored regions overlap at the number 3 and nothing else. So even though this was an inequality problem, you might be tempted to say this for your answer. The answer is t equals 3, and that's kind of right. But remember, most of the time they want interval notation. And interval notation for this situation is kind of tricky. It uses a symbol you don't typically see in interval notation. It uses the curly parentheses. So the reason I showed you this example was to point out that in interval notation, you eventually use every type of parentheses. Round parentheses, square parentheses, and, like in this example here, curly parentheses.